Hello and welcome to LSAT Logic Applied. I'm your host, Andrew Leahy, an assistant teaching professor of law at Drexel Klein School of Law. This is a short format podcast where I take the tools from LSAT Logical Reasoning, assumptions, flaws, causation, strength, and weaken, and apply them to real-world claims in the news, science, and public discourse. For those that don't know, the LSAT is the law school admission test, a standardized exam designed to assess logical reasoning, analytical thinking, and reading comprehension for law school applicants. It's a high-stakes test with a unique focus on how arguments work and how they fall apart. The LSAT is owned and administered by the Law School Admission Council, or LSAC. I don't claim any affiliation or ownership. I'm just here to teach the logic. And you don't need to be studying for the LSAT to follow along. The point is to learn how to spot weak or incomplete reasoning in everyday life. The same kind of reasoning the LSAT trains you to attack under time pressure. Today's episode looks at a claim in science that a lab-engineered diet may dramatically improve bee colony health and potentially help save our food supply. We're not evaluating whether bees need nutrients or whether colony collapse is a real issue. We're evaluating how the argument connecting this new diet to large-scale outcomes is constructed. Here's the background. A group of researchers working across institutions, including the University of Oxford and the Royal Botanic Gardens, developed a synthetic diet for honeybees. The key insight is nutritional. Bees rely on pollen, which contains essential lipids called sterols, compounds critical for growth and development. But due to climate change and intensive agriculture, bees increasingly lack access to diverse pollen sources. Standard artificial feeds give them calories, but not the full set of sterols they need. So researchers engineered a yeast, Yaroia lipolytica, using CRISPR to produce a precise mix of 6 essential sterols. They added this to the bees' diets and tested it in controlled glasshouse environments. The results were striking. Colonies fed the enriched diet produced up to 15 times more larvae reaching the pupal stage. They also continued producing brood longer than control colonies, and from this, researchers and commentators suggest something broader, that improving bee nutrition through engineered supplements could significantly strengthen bee populations and potentially stabilize food production systems that depend on pollination. At first glance, this is exceedingly compelling. There's a clear mechanism, a controlled experiment, and a dramatic observed effect. But before we accept the broader claim, let's apply some LSAT logic, because the key question isn't whether the result is impressive. It's whether the conclusion being drawn is fully supported. The structure of the argument looks something like this. Bees need specific sterols for proper development. Modern environments often deprive them of those sterols. A lab-engineered diet restores those missing nutrients, and in controlled experiments, colonies fed this diet grow dramatically faster. Therefore, providing this diet could significantly improve bee populations and help protect global food systems. That seems plausible on its face, but on the LSAT, this is exactly where we have to slow down because the argument moves from a controlled experimental result to a broad real-world conclusion. So let's start with the core causal claim. The study shows that adding sterols improve colony growth in a controlled environment. That shows strong evidence of a causal relationship in that setting. But the broader conclusion assumes that nutrition is a primary limiting factor in real-world bee populations. In reality, bees face multiple stressors: parasites, pesticides, disease, habitat loss, and climate effects. On the LSAT, this is a classic issue. Even if one factor has a causal effect, it may not be the dominant factor in the real world. Improving nutrition may very well help, but not necessarily at the scale implied. And next, let's consider the experimental setup. The study was conducted in controlled glasshouse conditions where bees consumed only the experimental diet. That isolates the variable, but also simplifies reality. In the wild, bees forage across mixed environments, encounter toxins, compete with other species, and face fluctuating conditions. On the LSAT, this raises a key question. Does the result generalize beyond the controlled setting? A result that holds in isolation may weaken or disappear under real-world complexity. And notice also that there's some scope shift. There's a jump in the conclusion. The study shows a 15-fold increase in larvae under specific experimental conditions. The broader claim becomes this could help save bee populations and, by extension, global food supply chains. That's a major expansion in scope. On the LSAT, this is a common flaw, moving from a narrow, specific finding to a sweeping systemic conclusion without sufficient bridging evidence. We also have a bit of an issue of mechanism versus sufficiency. The researchers have clearly identified a mechanism. Sterols are essential, and this diet supplies them. But identifying a necessary component is not the same as showing sufficiency. Even if sterols are required for healthy development, providing them alone may not solve the broader problem. On the LSAT, this is the difference between this is part of the solution and this is enough to solve the problem. Necessary versus sufficiency. And then finally, we have selection effects. Let's consider what's being emphasized. The headline result is dramatic: 15 times more larvae. But we should ask, how consistent was that effect across trials? What happened in less successful cases? What happens over longer time horizons? If the most striking outcomes are highlighted while variability is downplayed, the argument may rely on a selective presentation of results. That's a classic LSAT concern, cherry picking the most favorable evidence. So, what's missing here? If we wanted to strengthen this argument, what would we want to know? Well, we'd want to know whether similar gains occur in large scale field trials under real world conditions, whether improved nutrition meaningfully offsets other major threats like pesticides or disease, and whether colonies receiving the supplement show sustained survival and reproduction over time, not just short term growth. On the other hand, the argument would be significantly weakened if field results show much smaller effects, other stressors dominate colony decline regardless of nutrition, or long term outcomes fail to match the short term experimental gains. In other words, the key issue is not whether the mechanism works, it's whether it scales. This episode isn't really about bees. It's about how we evaluate scientific breakthroughs, especially when the results are dramatic and the implications are large. On the LSAT, that's exactly where the hardest questions hide. The real issues are, does the effect generalize beyond the lab? Is the cause sufficient or just one piece of a larger system? And does the evidence support the full scope of the conclusion? Scientific advances often come with compelling narratives, clear mechanisms, strong results, and really big implications. But logic asks a more disciplined question. Does the evidence actually support the claim that is being made? Thanks for listening to LSAT Logic Applied. If you enjoyed this breakdown, subscribe for more short episodes where we apply clean logic to messy real-world claims. See you next time.